This is going to be the lecture over chapter 29, section 1. We're going to be discussing electrons and atoms. Now, this discussion of how electrons appear in atoms is going to be far beyond what you've normally seen up to this point, because the planetary model is insufficient to actually describe what is going on. So how do we look at it? Well, the Bohr model here, it doesn't describe atoms very well because it combines elements of classical physics along with quantum mechanics. Now, you might not think that's a bad thing, but unfortunately, it's just simply inadequate in order to be able to describe fully what is taking place. So to explain what we actually observe, we come up with something called a wave function. And that is determined by solving something called the Schrodinger equation. Now, that's not something we're going to really get into that deeply. But the Schrodinger equation is really an equation that allows you to be able to determine with some probabilities as far as what the state of the atom is going to be. And we'll go ahead and we'll leave it at that. As a result, some properties of the atom are going to be quantized. This includes orbital and spin angular momenta. The quantum numbers n, l, m sub l, and s specify the quantum mechanical states of the atom, and according to the Pauli exclusion principle, no two electrons in an atom can occupy the same state. So let's go to this section. Let's see what we got here. Okay. So from the classical description of particle motion in terms of 3 coordinates and 3 velocity components, that can't be applied to motion on an atomic scale. It just won't work. In some situations, electrons behave like waves rather than particles, and their wavelength can be measured by diffraction experiments. So we're going to need to develop a description of the electron and its motion that incorporates the idea of a spatially spread out entity, which is somewhat counterintuitive to our approach thus far. So we're going to take a look or borrow a little bit from classical wave motion in order to be able to make this happen. So earlier, back in chapter 12, if you remember back that far, we described the motion of transverse waves on a string by specifying the position of each point on the string at each instant of time. And we had a function that would do that. That wave function was what we needed in order to be able to say, hey, the wave is here at a certain point, it's over there at a certain point, and that kind of thing. So if a point on the string is at some distance x from the origin, it's displaced transversely a distance y from its equilibrium position at some time t. And then you've got a function that describes that. So once we know the wave function that describes a particular wave motion, we can find the position, velocity, and acceleration at any point on the string. So by adapting the language of waves to describe the motions of electrons and atoms, we end up using a wave function that is the central element of the generalized language for describing the possible dynamic states of electrons. The symbol used for this is going to be psi. So for a single electron, psi is a function of the spatial coordinates as well as time. And for a system with many electrons, it's a function of all the space coordinates of all the particles and time. And so just as the wave function for mechanical waves on the string provides a complete description of the motion, the wave function for a particle contains all the information that can be known about the dynamic state of that particle. So now we end up with two questions. So first, how do we relate the wave function to the observable behavior of the particle? And second, how do we determine what psi is for any particular dynamic state of the system? So for the first question, the wave function describes the distribution of the particle in space. And it's going to be something that looks like a cloud. It's going to be more dense in some regions and less dense in others. And the wave function is related to the probability of finding the particle in each of the various regions. In other words, each part of the region is going to have a probability that the electron is there. So the particle is most likely to be found in regions where psi is large. We've already used this interpretation in discussion of electron diffraction experiments. If the particle has a charge, the wave function can be used to find the charge density at any point in space. So in addition, from psi, we can calculate the average position of the particle, its average velocity, and dynamic quantities such as momentum, energy, as well as angular momentum. And if we wanted to get into the math of this kind of stuff, it's going to go beyond most likely the types of math that you have been exposed to up to this point. So we're not going to do that here. What you're going to see here are cross sections of wave functions for three possibly spherical symmetric states of a hydrogen atom. And now there's no possibility of actually seeing this distribution since the atom is much smaller than the wavelengths of visible light. We're just drawing this in order to be able to get a picture of what's going on. So you can see here, if we take the function for psi, which you do not see here, but if you were to see it, basically you would see that the probability drops off quite a bit as the length of the radius goes out. So if you're looking at something that's in a quantum state here, 1s, you're much more likely to find the electron here than where you would when it starts to fade out. If you look at it here for a 2s model, you're going to see here that you have a probability of finding it close in. Then as you go a little bit further out from the radius, you will find that there is a section here where you don't have much of a probability of seeing it at all. And then it ramps back up again. And so out here, you will see that probability exist again for seeing the electron there. Same thing here with the 3s model. And then you can start to see the ring formations here as you go out. So the answer to the second question, again, the second question being, how do we determine what psi is for any particular dynamic state of the system? The wave function must be one of the sets of solutions of a certain differential equation, which again, we're not going to go through. That Schrodinger equation was developed by Erwin Schrodinger in 1926. The principle, we can set up a Schrodinger equation for any given physical situation. The wave functions that are solutions of this equation represent various possible physical states of the system, which are the analog of the orbits in the Bohr model. And furthermore, it turns out that for many systems, it's not even possible to find acceptable solutions of the Schrodinger equation unless some physical quantity, such as energy, has certain specific values. Thus, the solutions of the Schrodinger equation for any particular system also yield a set of allowed energy levels. This discovery is of utmost importance. Before the development of the Schrodinger equation, there was no way to predict energy levels from any fundamental theory, except for the very limited success of the Bohr model for hydrogen. So you need a model that's bigger and better than that. So soon after the Schrodinger equation was developed, it was applied to the problem of the hydrogen atom, and the predicted energy levels turned out to be identical from those of the Bohr model. So that's a good indication. These results also agreed with experimental values obtained from spectrum analysis. In addition, the solutions have quantized values of angular momentum. So just as in section 10.7, angular momentum is fundamentally a vector quantity. In the Bohr model, the angular momentum is a vector perpendicular to the plane of the electron's orbit. So the quantization of angular momentum was put into the Bohr model as an ad hoc assumption with no real fundamental justification. With the Schrodinger equation, it appears naturally as a condition for the existence of acceptable solutions. Specifically, it is found that for an electron in a hydrogen atom in a state with energy E sub n and quantum number n, acceptable solutions of the Schrodinger equation exist only when the magnitude L of the vector angular momentum is given by these expressions. So these possible values of angular momentum for the electron of the hydrogen atom are this, depending on what the value of L happens to be. And the component of L in a given direction, say the Z component, can only have set values. So you can see those here. And you can see all of these values listed here. M sub L is going to be your magnetic quantum number. L is going to be the angular momentum quantum number. So instead of a single quantum number, as in the Bohr model, the possible wave functions for the hydrogen atom are labeled according to the values of 3 integers. And so these are called the principal quantum number and the angular momentum quantum number L and the magnetic quantum number M sub L. There's also a 4th quantum number associated with spin, and we'll get to that here in just a second. So for each energy level, E sub n, there are several distinct states that have the same energy and the same value of n, but different values of L and M sub L. So in other words, your angular momentum quantum number and your magnetic quantum number are going to be different. The only exception is going to be the ground state, for which n is equal to 1, and the only possibility for the other 2 quantum numbers is L is equal to 0 and M sub L is equal to 0. So for any value of n, L can be no greater than n minus 1. The term magnetic quantum number refers to the slight shifts in energy levels that occur when the atom is placed in a magnetic field. These shifts are different from states that have the same N and L, but different values of M sub L. So the quantity h over 2 pi appears so often in quantum mechanics that basically what they're going to do is they're going to change that h divided by 2 pi, and they're going to call it h bar. And this is going to be your value here. So rather than write this, they're going to write this. So note that the component L sub Z can never be quite as large as L. So for example, when L is equal to 2 and M sub L is equal to 2, you go through and you find these values. And the angle between the vector is going to be given as follows. So you see that theta there, the value is going to be 35 degrees. So that's what they're trying to drive at here. So you've got a figure here where you got the magnitude and the components of angular momentum. And then you've got the magnitude and components of angular momentum down here as well. It's just more of in a 3D motion. So you can see here that you've got the Z component and then you've got the angular momentum component. And you can see how those two are here. What is the angle here in between this and this? Well, depending on what the values here of this and this are, then this determination can be made. So we don't know the precise direction of L. It can have any direction on the cone there in the figure of angle 35 degrees. So it could be anywhere on that particular cone. This result also follows from the uncertainty principle, which makes it impossible to predict the direction of the angular momentum vector with complete certainty. So figure 29.2 shows the angular momentum relationships for the particular states with L is equal to 2. In each state, these have definite values, but the component of L perpendicular to the z-axis does not. We can only say that this component is confined to a cone of directions. In other words, we can't hold it down any further than that. Electron spin. All atoms show shift or splitting of their energy levels and spectral wavelengths when placed in a magnetic field. This isn't surprising. Electric charges moving in a magnetic field are acted upon by forces, but some atoms show unexpected shifts even when no magnetic field is present. So in 1925, it was suggested that perhaps the electron should be pictured as a spinning sphere of charge rather than an orbiting point charge, concept called electron spin. So if that is true, the electron not only has angular momentum associated with its orbital motion, but also additional angular momentum associated with the rotation on its axis. The resulting additional magnetic field interactions might cause the observed energy level anomalies. So in other words, here's an analogy. The Earth travels in a nearly circular orbit around the sun. Now, at the same time, it rotates on its axis. Each motion has its associated angular momentum, which we call the orbital and spin angular momentum, respectively. The total angular momentum is going to be the vector sum of the two. Precise spectroscopic analysis, as well as a variety of other empirical evidence, has shown conclusively that the electron does have angular momentum that doesn't depend on its orbital motion, but is intrinsic to the particle itself. Like orbital angular momentum, spin angular momentum, usually denoted by S, is found to be quantized. So suppose we have an apparatus that measures the component of S in a particular direction, say the z-axis, denoting the z component by S sub z, we find that the only possible values are plus 1/2 or minus 1/2 times h bar. It's very much due or similar to equation 29.4, where the z component of orbital angular momentum, but the magnitude of S sub z is 1/2 of h bar instead of some sort of integer multiple. So an electron is often called a spin 1/2 particle. The magnitude of the spin angular momentum is going to be given by this formula. So in quantum mechanics, in which the Bohr orbitals are superseded by wave functions, we cannot really picture an electron as a small object that spins. But if we visualize the electron wave function as clouds, then we can imagine many tiny arrows distributed throughout the cloud, all pointing in the same direction, either plus z or minus z. But take that with a grain of salt. In any event, the concept of electron spin is well established by a variety of experimental evidence. To obtain completely the state of the electron in the hydrogen atom, we now need a fourth quantum number, as if you needed something else to worry about, which is going to be the spin quantum number. It specifies the electron spin orientation. So if S can take the value of 1/2 or minus 1/2, then the z component of the spin angular momentum is given by this. So the possible states of the electron and the hydrogen atom are labeled with a set of 4 quantum numbers. Principal quantum number n determines the energy, and the other 3 quantum numbers specify the angular momentum and its components in a specified direction, usually taken to be the z-axis. So you can see different clouds here that are created with different combinations of quantum numbers. Kind of weird stuff. So the hydrogen atom with one electron and a nucleus containing a single proton is going to be the simplest. All other electrically neutral atoms contain more than one electron. The analysis of atoms with more than one electron increases the complexity very rapidly. So each electron interacts not only with a positively charged nucleus, but also with the other electrons. In principle, the motion of the electrons is still governed by the Schrodinger equation, but the mathematical problem of finding appropriate solutions of that equation is so complex that it has not been solved exactly even for the helium atom. So don't even try it with, xenon or some of the other humanly manufactured elements that don't stick around for very long. Various approximation schemes can be used to apply the Schrodinger equation to multi-electron atoms. The most drastic is to ignore the interactions of the electrons with one another and assume that each electron moves under the influence of only the electric field of the nucleus, which is considered to be a point charge. So a less drastic and more useful model is to think of all the electrons together as making up a charge cloud that on average is spherically symmetric. In that model, each individual electron moves under the action of the total electron field due to the nucleus and this averaged out electron cloud. Turns out that when an electron moves an electric field produced by a spherically symmetric charge distribution, the angular momentum states that given by the quantum numbers are exactly the same as those of the hydrogen atom. So this model is called the central field approximation. It proves useful as a starting point for the understanding of the structure of complex atoms. The energy levels now depend on both N and L, usually for a given value of N. The levels increase in energy with increasing L, but individual levels can still be labeled by the set of 4 quantum numbers with the restrictions as before. So you can see all of these restrictions here. The exclusion principle. So to implement the central field approximation, we need one additional principle, and this is the exclusion principle. So to understand the role that this plays, we need to consider the lowest energy state or ground state of a multi-electron atom. In this central field model, which ignores interactions between electrons, there is a lowest energy state corresponding to n is equal to 1 for the single electron in the hydrogen atom. Might expect that in the ground state of the complex atom, all the electrons should be in this lowest state. If so, then the behavior of atoms with increasing numbers of electrons should show gradual changes in physical and chemical properties as the number of electrons in the atom increase. So a variety of evidence shows conclusively that this is not what happens. So the elements fluorine, neon, and sodium all have 9, 10, 11 electrons per atom. Fluorine is a halogen. It tends strongly to form compounds in which each atom requires an extra electron. Sodium, an alkali metal, forms compounds in which it loses an electron, and neon is an inert gas that ordinarily forms no compounds at all. So these observations and many others show that in the ground state of a complex atom, the electrons cannot all be in the lowest energy states. So the key to resolving this puzzle was determined by Wolfgang Pauli in 1925. And it says that no 2 electrons in an atom can occupy the same quantum mechanical state. Alternatively, no 2 electrons in an atom can have the same values of all 4 of those quantum numbers. So different quantum states correspond to different spatial distributions, including different distances from the nucleus and to different electron spin orientations. So roughly speaking, in a complex atom, there isn't enough room for all the electrons in the states nearest the nucleus. Some electrons are forced by the Pauli principle into states that are further away with higher energies. So now we can make a list of all the possible sets of quantum numbers and thus of the possible states of the electron and the atom. And that's going to be given in this table, which also indicates two alternative notations. And it's customary to designate the value of L by a letter according to this scheme. So you can see here, you've got N. This can range all the way up to N minus 1, so its only value is 0. This can range from L to minus L, so the only value is 0. In spectroscopic notation, you've got an energy level there of 1, and the value of L in this case, since it is 0, is going to be given by the letter S. And you have two states here. It's going to be one with a positive 1/2 spin, and then the other with a negative 1/2 spin. Shell is going to be in K. Then you can see the additional energy levels here. And then you can see they go from 2, 3, 4 on up. You can also see the values of L. Let's see, I think I said, yeah, that should go up to N minus 1. Yeah, that's right, I said that. This can go from a minus L up to L with integer values only. You can see that here, and you can see the number of states that go along with that. This peculiar choice of letters occurred in the early days of spectroscopy and really has no fundamental significance. A state for which N is equal to 2 and L is equal to 1 is called a 2p state. And so the table, which also shows a relationship between the values of N and X-ray levels, that we'll look at in the next section. So with some exceptions, the average distance of the electron from the nucleus increases with N. Thus, each value of N corresponds roughly to a region of space around the nucleus in the form of a spherical shell. Hence, we speak of the K shell as the region occupied by the electron in the N is equal to 1 state, the L shell as a region of N is equal to 2, and so on and so forth. Each quantum state corresponds to a certain distribution of the electron cloud in space. Therefore, the exclusion principle says, in effect, no more than 2 electrons can occupy the same region of space. The wave functions that describe electron distributions don't have sharp, definite boundaries, but the exclusion principle limits the degree of overlap of electron wave functions that is permitted. And the maximum numbers of electrons in each shell are given in the table.